Here's a programme now for the course on the history of mathematics. It discusses the investigations in the 18th and 19th centuries by such mathematicians as Gauss, Bolyai and Lobachevsky of the parallel postulate of Euclid.
The consequences for mathematics are really momentous. Mathematics had been regarded as an unquestionable body of truths, and now mathematicians had to abandon one of what one might call the sacred traditions about mathematics. It is not a body of truths. It presents a body of alternatives, and we will use that alternative which, at any one time, seems best suited to our scientific description of the physical world.
What caused this decisive change in mathematical thinking was the creation of a non-Euclidean geometry, a geometry that differed from Euclid's assumptions in only one respect: parallel lines. In Book 1 of his Elements, Euclid proved that any two angles in a triangle add up to less than two right angles. But the converse, that if these two angles are together less than two right angles, then these lines meet and form a triangle, could not be proved. Euclid had to assume it instead. Now, this was very disturbing. Let's briefly see why. Let's take two triangles with their corresponding angles equal. Triangles like these are said to be similar. That is, they have the same shape. If, in addition, they have the same size, then they're said to be congruent. Now, there's an immediate connection between similarity and proportion, and between similarity and parallels, as you can see. So, without a postulate guaranteeing properties of parallel lines, there are serious problems. You can't even prove, for example, that the angles in a triangle add up to 180 degrees. This theorem is essential for many elementary proofs in Euclidean geometry. But you know, we've even got problems with proving angles to be equal, unless we can be quite sure that straight lines can't approach each other indefinitely without eventually meeting. This is something that Euclid had to assume. But many mathematicians, Greek, Arab, and later on European, tried to deduce it, or something equivalent to it, from the other axioms.
Well, that line of attack, which was pursued by many mathematicians over hundreds of years, did not succeed. And then another line of attack was developed by a Jesuit priest known as Girolamo Saccheri in the early 18th century. Saccheri's idea was to deny the Euclidean parallel axiom in the form, using the form I have just stated, and to hopefully obtain contradictions.
If there isn't just one parallel through P to a line, then there may be many. Or there may be none. By considering sums of angles, Saccheri effectively took each case in turn. The hypothesis of no parallels, he showed it led to a contradiction. And so he rejected it. The hypothesis of many parallels? Well, Saccheri thought he had also refuted this, but here he was mistaken. Left only with the classical postulate of one parallel, he published his defense of Euclid in 1733.
However, later mathematicians realized that Szekely had not, in fact, deduced a contradiction by using the assumption of many parallel lines through the point P. And these men did follow up the consequences of using that axiom in place of the Euclidean parallel axiom. And they produced a number of interesting theorems. For example, in this geometry, which was later called hyperbolic geometry for reasons which are rather irrelevant, it turns out that the sum of the angles of a triangle is always less than 180 degrees. Moreover, the sum of the angles comes closer to 180 degrees as the area of the triangle becomes smaller, so that for a small triangle one would have difficulty in distinguishing the two geometries on the basis of the angle sum. Another very interesting theorem in this hyperbolic geometry is that if two triangles are similar, that means if the angles of one are equal respectively to the angles of the other, they are necessarily congruent. And there are many other strange theorems in this hyperbolic geometry. However, up to about 1800, while some mathematicians, rather few, were willing to admit that there could be this alternative geometry, it was regarded as a logical curiosity, having very little real significance. The most significant step in the history of non-Euclidean geometry was made by that monumental mathematician Carl Friedrich Gauss. Gauss, too, worked on the problem of the parallel axiom. And he, too, had failures in attempting to deduce it from the other 9 axioms. And then he examined critically this hyperbolic geometry of Szekely. And Gauss not only recognized, as a few others had before him, that this geometry was certainly a logical possibility, but he reached the startling conclusion that this geometry could be as physically applicable as Euclidean geometry, as true, in other words, of physical space as Euclidean geometry was. There is a famous statement by Gauss which comes from a letter he wrote to his friend, the Hungarian mathematician Wolfgang Bolyai. And he says in 1799, "As for me, I have already made some progress in my work. However, the path I have chosen does not lead at all to the goal which we seek." And he meant by that deduction of the parallel axiom from the other 9 axioms, and which you assure me you have reached. It seems rather to compel me to doubt the truth of geometry itself. And what Gauss meant by the truth was the necessary physical applicability of non-Euclidean geometry, this particular hyperbolic geometry. Though Gauss was convinced not only of the logical soundness of hyperbolic geometry and of its possible physical applicability, he didn't publish his ideas. It's rather interesting that a man with Gauss's reputation feared that his colleagues would consider him mad. So deeply ingrained was the conviction that Euclidean geometry was the only possible description of physical space and of the properties of figures in physical space, that Gauss was quite certain his colleagues would not accept it. However, he did communicate his ideas in letters to friends. And through these letters, 2 other men, Nicholas Lobachevsky, who was first a student and then a professor at the University of Kazan in Russia, and Johann Bolyai, who was a Hungarian army officer, did accept Gauss's ideas and published their versions of hyperbolic geometry. What they published was essentially what I described earlier, and what, in fact, Saccheri had really done, despite the fact that Saccheri drew the wrong conclusion from what he did. And so the world became aware, through publications, of this hyperbolic geometry through the writings of Lobachevsky and Bolyai. Often these two men are given the major credit for the creation of hyperbolic geometry, though, in my own opinion, Gauss was the man behind all of this work.
Lobachevsky and Bolyai's approaches were strikingly similar. First of all, they both started by considering that the parallel postulate was true, but they began to have doubts by the early 1820s. Lobachevsky's first exposition of his geometry was in a lecture in 1826, but unfortunately the manuscript is lost. But we do have his second exposition in a memoir of 1829. For him then there began a long and unsuccessful attempt at getting his geometry accepted. But even though he published in French and German as well as in Russian, there were few who were interested. He was also unpopular for his liberal views, and he died blind and neglected in the end in 1856. Bolyai seems to have been confident of the possibility of a non-Euclidean geometry by as early as 1823. He'd been studying the theory of parallels for some years, and against his father's advice. His father was himself a mathematician, and researches on these lines had been described as the ruin of his life. But the younger Bolyai wrote to his father, "The goal is not yet reached, but I have made such wonderful discoveries that I have been almost overwhelmed by them, and it would be the cause of continual regret if they were lost. When you will see them, you too will recognize it. In the meantime, I can say only this: I have created a new universe from nothing." In 1831, Bolyai's work appeared as an appendix to his father's geometry, and when a copy reached Gauss, he wrote as follows: "If I commenced by saying that I am unable to praise this work, you would certainly be surprised for a moment. But I cannot say otherwise. To praise it would be to praise myself. But I am very glad that it is just the son of my old friend who takes the precedence of me in such a remarkable manner." Gauss's response so offended Bolyai that he never published again, though he continued to study mathematics until his death in 1860.
Another development in the area of non-Euclidean geometry ultimately proved equally significant. A student of Gauss, Bernhard Riemann, subsequently a great mathematician in his own right, took up the subject of non-Euclidean geometry. In the course of a general investigation, about which I shall say more in a moment, he made a distinction between an unbounded line and an infinite line. That distinction is best illustrated by considering the equator of the Earth. We see that the equator is an unbounded line. One can keep traversing it endlessly without reaching an end. On the other hand, we know that the length of the equator is finite, in fact, about 25,000 miles. Other people took up this idea that we must change our notion of the straight line, and by incorporating also the axiom that there are no parallels to a given line through a given point, produced another non-Euclidean geometry, now called, for reasons which are irrelevant, elliptic geometry.
Let's think of the Earth for a moment as a sphere, and let's define our straight lines on it to be the curves of shortest length, great circles as we call them, such as the equator or the Greenwich meridian. Well, now we can illustrate some of the theorems of elliptic geometry. For example, you can see that in this triangle, the angles must add up to more than 180 degrees, because both these are right angles, and there's this angle to add in as well. And also, in fact, similar triangles are necessarily congruent. But this spherical geometry was well known at the time, and in fact it guided research into non-Euclidean geometry in both the 18th and 19th centuries. So why was it that it was never actually considered to be a non-Euclidean geometry in its own right, and so an answer to this parallel problem? Well, we'll say something about this later on, but bear it in mind as we proceed.
Well, we now have a third geometry, and the question of the applicability of this geometry to physical space was also raised. Again, no decision could be made on the basis of measurement. And so we now have three candidates, three geometries, which might all be equally applicable to physical space. There is another historical curiosity here, which is characteristic of many developments in mathematics. I have said that Bolyai and Lobachevsky published developments of hyperbolic geometry. Sakari, we may recall, concluded incorrectly that there were contradictions in this geometry. Bolyai and Lobachevsky did not believe there were any contradictions. However, they had no proof that if they continued to prove theorems, that they would not arrive at theorems that contradicted previously proven theorems. This problem is known as the problem of consistency. That is, how do we know that a branch of mathematics will not produce contradictions if carried far enough? Well, it is interesting that the mathematicians who accepted non-Euclidean geometry for a long time, those who did at least, accepted it without any proof of the consistency, something that really they should not have done. Fortunately, the consistency of non-Euclidean geometry was established largely through the use of models. One of these models was suggested by an Italian mathematician, Eugenio Beltrami, and the model is known as a pseudosphere. On this surface, if we take straight lines to mean the shortest distances between any 2 points, the properties of figures on this surface obey the theorems of hyperbolic geometry. For example, the sum of the angles of that triangle will be less than 180 degrees, and in fact will vary with the size of the triangle.
Now, we've already seen that a model of elliptic geometry is provided by the sphere, so long, of course, as we interpret straight line to mean great circle. Now, we get a great circle whenever we take a plane slice which passes through the center of the sphere. And so all longitudes are great circles, but there are many others, such as this one, for example. Now, you'll notice straight away that any two great circles have got to meet. But they meet, in fact, twice. In this case, again, over here. And any two common perpendiculars to a given line, such as here and here, where these two lines are common perpendiculars to the equator, well, they're going to meet as well, as they do at the top. And that's contrary to what happens in Euclidean geometry.
Well, the pseudosphere and the sphere are figures in Euclidean space. If there were any contradictions in hyperbolic geometry or elliptic geometry, there would have to be contradictory theorems applying to the pseudosphere and to the sphere. But as figures in Euclidean space, if Euclidean geometry is consistent, there cannot be any contradictory theorems holding about the pseudosphere and the sphere. So that the proof of the consistency of these non-Euclidean geometries really depends upon the proof of the consistency of Euclidean geometry. But at this time in the history of mathematics, no mathematician would have dared to question the consistency of Euclidean geometry.
Let's now think where all this is leading us. We can ask with Lobachevsky and Bolyai if the space in which we actually live is Euclidean or not. This may seem a rather strange question, but that's just because we're so used to seeing the space we live in as a Euclidean space. But we don't have to. Every time we look into a curved mirror, for example, the world that we see in it is distorted and non-Euclidean. If we draw our Euclidean figures as they'd appear in a curved mirror, then we'd be led to a non-Euclidean geometry. But how do we know that space isn't curved anyway? Perhaps what we see is distorted without us knowing it, from a curved non-Euclidean space into our familiar flat Euclidean one. Well, once new geometries became possible, the idea that they might be physically true as well couldn't be rejected.
To get back to Riemann, Riemann went farther. He, of course, was fully aware of these three geometries, but he also envisioned even more general non-Euclidean geometries, which today are more commonly referred to as Riemannian geometries. I can perhaps explain Riemann's idea by asking you to imagine a mountainous area. High mountains, low mountains, and perhaps even flat surfaces. The geometry of such an area will vary from place to place. That is, the properties of figures will vary from place to place. Where Riemann considered such what are called non-homogeneous geometries. That is, the non-homogeneity referring to the fact that the properties of figures depend upon where you take those figures, whether you take them on a flat area or on the side of a mountain or on the top of a mountain. And so we have really many non-Euclidean geometries. The mathematicians did not take to these new ideas very kindly or very quickly. And most mathematicians, right up to 1900, refused to believe that these non-Euclidean geometries, or even less likely the more general Riemannian geometries that I described briefly earlier, would ever be physically applicable. But science made a difference. In 1905, Einstein published his special theory of relativity, in which he used a rather limited kind of non-Euclidean geometry. And then in 1915, he published his general theory of relativity, in which he used one of these very elaborate Riemannian geometries, one of these inhomogeneous geometries that I described earlier. Mathematicians were now forced to face the fact that in the best scientific theory to date, meaning, of course, the first decades of this century, non-Euclidean geometry had to be taken as the best description of physical space. Of course, science proposes theories, and theories change from time to time. And it could very well be that at a later date, another kind of geometry would have to be employed.